talking about salinity in our oceans. So salinity in our oceans, as you probably know, is measured in something called parts per thousand. And all that means is that we're going to measure things for how many parts salt there is, or ions, per 1,000 parts salt water. So if you know that 1 kilogram is 1,000 grams, when we talk about salinity for seawater, our average is about 35 parts per thousand, which means that there are in our seawater an average of about 35 grams of dissolved salts or ions per our 1,000 parts seawater. Now, when we say salts, predominantly those salts, those 35 grams per 1,000 or 1 kilogram of seawater, those 35 grams of dissolved salts are going to be things like predominantly sodium and chloride, which is what you would think of, right? Which is your table salt. But there's going to be other ions in there as well. There's not just sodium and chloride. It's not just like you can take sodium and chloride and that makes your seawater, right? So there's other ions in there. There's also magnesium, there's sulfates, there's calcium, there's potassium, there's bromine. So there are other ions mixed in. You don't need to know all those ions. I just like to tell you that. So when we're talking about salinity, you know that it's just not your table salt and water. There are other ions dissolved within that water. So again, when we're talking about salinity, I love this diagram. I snagged this from the internet for you guys because it shows you what fresh water looks like versus, saline water versus like briny water. And when you look at fresh water, you're talking about like ponds, lakes, rivers, and streams. You're talking about anywhere from 0 to only 0.5 parts per thousand. So again, very small amount. You're talking about like 0.5 grams of salt per 1,000 parts water. So that's going to be your fresh water, okay? And then when you talk about your brackish water, we're going to talk about estuaries, mangroves, things like that, where you have kind of freshwater, saltwater mixing. That brackish water will be anywhere from 0.5 parts per thousand to 30 parts per thousand. So a really wide swing and salinity in here. And though these environments really have to be well adapted for both kind of fresh and saltwater conditions. So we'll talk about that in those estuarine communities when we get there. Then we have, again, our saltwater communities, which is anywhere from 30 to 50 parts per thousand. But on average, when we talk about seawater, it's going to be 35 parts per thousand for salinity. So that's your average seawater. You can see, again, the Red Sea is going to, be much more saline at 40 parts per thousand, but average is 35. And then when you're talking about like your briny pools, where you have like your brine shrimp and things like that, that's like up near 50 parts per thousand. So pretty drastic change there in salinity. Okay, so let's get into this. Again, average salinity for the ocean is 35 parts per thousand, or again, 35 grams of dissolved salts per 1 kilogram of seawater. So it's important that you know that average salinity for the ocean and that it's measured in parts per thousand, what that is. And if you look here, percent is parts per hundred, right? So percent is just the 10. So when you do the shorthand, the symbol for parts per thousand, instead of it being parts per hundred, it's parts per thousand. You add 2 zeros there. So kind of cool. Easy, right? To remember that. So, I didn't mean to go there. So how does salinity increase? Okay, so there are two major ways in which salinity increases. One is that when you get evaporation, when water evaporates, right, and moves into the gaseous form because the water molecules are so heated up and excited, they leave the salt behind. So that interaction between the water molecule and the ion breaks and the water molecule is freed and it leaves that salt behind. So that increases the salinity of the water. So if you have a lot of evaporation coming off of the surface of the water, that will make that body of water more saline. Freezing does the same thing. So as water freezes, those water molecules freeze at the surface. Those water molecules are going to leave the salt behind because those water molecules are going to form those nice hexagonal crystalline patterns, and they'll leave that salt behind. So evaporation and freezing are both going to be situations where the water molecules are going to interact or literally evaporate and become gaseous and leave the salt behind. And that will increase the salinity of the body of water that's left behind there. How is salinity decreased? Just the opposite, right? So now, in this case, instead of water, right, either leaving or freezing and forming that crystalline pattern and leaving the salt behind, now, instead, this situation is where you have to have some input of water. So precipitation, right? So rain water is going to be input of fresh water, and that will decrease your salinity. So precipitation is going to be one of the main ways that salinity is decreased. If you're like in a bay area, then you sometimes will get an input of like a stream, freshwater stream, and that will decrease the salinity because you have an input of fresh water as well. So salinity is going to vary mostly at the surface, and that's going to be primarily due to precipitation, evaporation, and also freezing, right? That's all going to happen at the surface. So salinity is going to vary the most at the surface. And partially enclosed seas or bays are going to have much more extreme salinities than anywhere else. So places like the Red Sea, where it's really hot and dry and you get a lot of evaporation and not much precipitation. So because of that, you get a lot of evaporation, then that's going to leave a really saline body of water behind. And that's what the Red Sea is. So that's why the Red Sea has an average salinity of about 40 parts per thousand, really saline, dense. Now, the Baltic Sea is just the opposite. You get extensive river runoff into that area, that partially enclosed area. And because of that, you're going to get a lot of freshwater input, and that's going to have a salinity of about 7 parts per thousand. So again, those are some of your extreme in salinity. But again, the average salinity for most ocean basins is going to be 35 parts per thousand. So those are the extremes. I do have a fun video for you you can watch on the Red Sea. I'm not going to play it here because I have a couple other video clips that I think are really important for animation stuff. But interesting video. You can kind of pick through that video. And again, you can get to all these video clips either through Canvas and my extra resources, or you can also get to them directly through the PowerPoint. Just put it into the presentation mode, and then you can click on all the links. Okay, so let's talk a little bit about salinity and density. I do have a short video on this, and you can actually do a little demonstration, a little lab to help yourself remember this. But I actually recorded the video with my daughter when she was home quarantining, and we did this demonstration together. So this is kind of a fun, please watch that video if you have kids. You can actually do the demonstration. I walk you through how to do the demonstration. You can actually do it with your kids, which is kind of fun. So, and it only takes, a few minutes. I think the video is only 6 minutes on how to do the whole thing. So please watch that demonstration because we are not actually going to do the lab that we typically do with salinity and density and temperature. So it might help you to remember that the saltier the water is, the denser it is. And this is just, if you think about it, intuitive. If you have water and you shove some salt in between those water molecules, right, it's going to be more dense because now you're adding in that mass of the sodium and the chloride ions. So the saltier the water, the denser it is. Colder the water, the denser it is. Remember? From our previous lecture, that's because as water gets colder, not freezing yet, but approaching that freezing point as it gets colder and colder, the water molecules are going to pack in tighter and tighter, and that's going to increase the density per a certain amount of volume of water. So colder, saltier water is going to make denser water. So again, I do this little demonstration for you so you can see this cold, salty water will sit on the bottom and the warmer, fresh water will sit on top. So temperature changes in the ocean vary much more than salinity does. And so because of that, density is controlled more by temperature than it will be by salinity. So this is a great diagram out of your book. I really think it does a great job of showing you quite a bit of information here. So what you can see here is you're going to see the temperature change up to about 1,000 meters here is the most drastic, right? And so again, temperature is going to vary most at the surface. And you can see that here. So the temperature is going to kind of gradually decrease till you hit about 1,000 meters here. And then it stays pretty stable after that. So the water column is fairly stable after you hit 1,000 meters in depth. You can see that inversely related to that, as the water gets colder, right? And the water molecules pack closer together, you're going to see that the water is going to get denser. So we call this inversely correlated, right? As the temperature goes down, the density goes up. Okay, until we hit about 1,000 meters down. And then again, it stays pretty stable. So we can see here that because of this inverse correlation, temperature has a much larger impact on density than salinity. And also, the other reason for this is that salinity is really variable at the surface. I mean, it can even be variable seasonally, right? With like a rainy season versus a warm, dry season. So, again, salinity is going to change vastly at the surface. Your salinity may be much higher if you're getting a lot of evaporation. It's really hot, not a lot of precipitation. Here, salinity may be much lower if you're getting a lot of freshwater input, a lot of rain, or a lot of freshwater runoff. So again, salinity is going to really vary vastly at the surface. So here's some factors again influencing salinity. I really like this chart if you're a visual person because you do need to know what increases salinity versus what decreases salinity. And so sometimes these visuals help you remember, here on this half are things that are going to increase salinity. So evaporation of water, right? Leaving the salt behind. Freezing of water, again, as those water molecules freeze, they leave the salt behind. And that's going to increase salinity, okay? Where decreases in salinity are going to be an input of fresh water. So in the form of precipitation, or of rain or snow, sometimes just a mass amount of melting of ice. River runoff is going to decrease salinity. Sometimes even, groundwater flow to the ocean, of fresh water flowing to the ocean here can decrease salinity. So those are all factors that influence salinity. And hopefully this will really help you kind of remember. I'm a visual person, so I try to put as many visuals as I can in here for you guys. The other challenge here, of course, is that we have to think on this kind of three-dimensional level in terms of looking at the ocean. So salinity not only is going to change with, depth, but it's also going to change with latitude and with seasons. So here, when you look at salinity, you're going to look and you see that salinity is fairly low near the equator. And the reason that salinity is fairly low towards the equator is that we're going to get more precipitation than we are evaporation at the equator. So more freshwater input, more precipitation. Now, as we hit, and we'll talk about why this is with the trade winds here, as we hit 30 degrees north and 30 degrees south, which, as you know, are typically where we have our deserts. This is where we're going to get more evaporation than we are precipitation. So salinity is going to increase. So again, at 30 degrees north and 30 degrees south, we're getting more evaporation than we are precipitation. And then, of course, it's going to drop back down as we get more precipitation on the higher latitudes there. Okay. So again, remember, once we hit about 1,000 meters down, the water column is fairly stable. The temperature is not changing a lot, the salinity is not changing a lot, and the density is not changing a lot. So you're really pretty stable there. The latitudinal gradient of seawater, you guys already know. Again, it's going to be warmest at the equator, cooler again as it gets towards the poles. That's pretty easy. So I like this. Again, this is straight from your book. This is a great profile. And the reason that I like it is that it shows you that temperature is going to change not only with latitude, right? But it's also going to change with seasons. So, it gets really difficult in terms of planning if you're trying to, talk about preservation of certain species in an oceanic community, planning for all of these types of changes. Marine conservation is terribly complicated. And this is one of the reasons why. So profiles change not only with depth, so temperature changes not only with depth, but it also changes with latitude. Obviously, much warmer at the equatorial regions in the tropics than it would be in the polar regions at the surface. And then it also can change with seasons. So again, being much warmer temperatures at the surface in the summer versus, in the winter. So this makes marine conservation very challenging. So again, just kind of as a review, changes at the surface, processes affecting salinity are going to be precipitation, evaporation, freezing, and they're going to occur at the surface. Also, again, you can have freshwater input from, rivers and river runoff, groundwater, things like that. The temperature changes also occur mainly at the surface, okay? And once the surface water has sunk, salinity and temperature don't change much. So we call that a water mass. So once we hit about 1,000 meters down, we have this kind of water mass that sits, this colder water is going to sit down kind of below the warmer water, right? That's less dense on top. And so we call this a water mass. And now that water mass from, 1,000 meters down, that water mass can oftentimes be identified from different water masses in different areas and different ocean basins by its temperature as well as its salinity. So it'll stay fairly stable. So again, surface water tends to stay floating on the denser water below, and this creates stability in the water column from 1,000 meters down. The greater the difference in density between the surface and the deep, the more stable that water column will be. So, what stirs up the water column? And I will tell you that we want the water column to stir up. And the reason being is that what happens is as things in the ocean die, right? Dead and decaying matter, they're going to sink, right? So if we have this dead and decaying matter, right, things that fish and things like that are dying in the ocean, plankton are going to die and they're going to settle along the bottom, okay? And so the bottom, the deep oceanic bottom, the abyssal plains are going to have all these nutrients in the bottom of them. And so how do we stir up the water column and bring those nutrients up to the surface? And so there are all kinds of ways that we can do this. We'll talk about wind, we'll talk about storm waves, we'll talk about earthquakes, and we'll talk about things like upwellings and downwellings. So stirring up, some of the main ways that we can stir up the water column is one, by storm surges. So storm surges are just these large waves that are created by really strong windstorms. And I'll show you two really short clips on what a storm surge is versus a tsunami. A tsunami will be something that we will talk about at the end of this lecture. So I'll let you watch this. Possibly, maybe. Let me try that one more time. Okay, so that, oops, sorry about that. That is a storm surge. So again, storm surges are created by large waves. And I won't show you all of this video, but this is kind of interesting just to see how, I apologize because, let me turn this down here. I apologize because some of these do, of course, have advertisements that have to play. But if you want to see what a storm surge looks like, again, with these, strong winds pushing, you can see here is a situation where this is a storm surge. Again, created by a storm with large winds. So storm surges can be pretty detrimental. So I'll let you, if you want, you can watch the rest of that video. A poor cameraman gets knocked over. But that's a storm surge. Very, very different than a tsunami, which we'll talk about later in the lecture, which is actually large waves caused by underwater earthquakes. Okay, so those are some ways that the water column can be stirred up. We're going to talk about some other ways in which the water column can be stirred up in some of the mass circulation, water circulation patterns that we see in our oceans, creating our big oceanic currents and our oceanic gyres. Okay, so this next little part of the lecture, we'll be talking about the movement of nutrients, salinity, and temperature around the ocean basins. And to understand this, you have to understand the Coriolis effect. Now, I'm going to go through a few videos to demonstrate the Coriolis effect because I can't do it. I'm not with you in class, which I normally would bring some demonstrations. But I'll show you these video clips. If you already have a good understanding of the Coriolis effect, you can fast forward this section of the video. So the Coriolis effect is something that occurs because the Earth is round and it's constantly rotating, right? And anything that moves over its surface, including us, right? We are in constant motion, but anything that moves over the Earth's surface, so for example, something like an airplane, right, moving across the Earth's surface, tends to turn a little instead of moving in a straight line. Here they're showing you that with the path of a missile, right? So if you have a missile and you are going to shoot that missile off, it's going to curve. Its path will curve. It's not going to take off and go straight above. It'll actually curve because the Earth is in motion. And so the easiest way to picture this is to picture this if you try to throw a ball while you are on a merry-go-round. And if you're trying to hit this person with a ball, you'll find that you won't hit it because, again, you are already in motion, in this circular motion, and so your ball will arc. And so this is the Coriolis effect. Because the Earth is constantly rotating, there's this tendency of objects moving large distances across the Earth's surface to bend. This is important that you get this. To the right in the northern hemisphere and to the left in the southern hemisphere. Okay? So again, I'm emphasizing you need to know that the Coriolis effect is going to impact things in terms of moving large distances on the Earth's surfaces to bend them to the right in the northern hemisphere and to the left in the southern hemisphere. And this is going to include things like winds. So the other interesting thing is things that are at the equator have to travel faster and farther to make one revolution in a single day. So if you are living in an equatorial community versus living, up at like 50 degrees, northern latitude, if you're living in an equatorial community, you're actually moving faster every day. You're traveling faster to make that one revolution around every day. It's kind of interesting. But you don't feel that, right? Because the Earth is so large. So I want to play these Coriolis effect videos really quickly for you because I know for some of you, it's kind of a tough concept, the Coriolis effect, because it's not something we talk about often, even though it's very important. So here's the Coriolis effect. This is a nice little video on the Coriolis effect. Yeah, the Coriolis effect doesn't really influence trail. It's not enough of a big a body of water moving big distance. But I actually meant to have that as the second video, so I apologize. This is kind of the more simpler Coriolis effect video, and this just shows you a little bit, gets into how we're going to talk more about how the Coriolis effect is going to impact some of your major currents. So let me get into this short video real quick. Okay, so hopefully that video, oops, sorry about that, guys. So hopefully that video will help you understand the Coriolis effect a little bit. Again, minus the fact that I don't have the ability to do some of my demonstrations for you. So that's the idea of the Coriolis effect. And again, so these objects that are moving large distances are going to be pushed to the right in the northern hemisphere and to the left in the southern hemisphere, just like they were bent or arced on the merry-go-round demonstration. So how does the Coriolis effect impact your wind patterns? This is where it becomes really important. The winds in our atmosphere are typically going to be driven by the heat energy from the sun, right? And we're going to get the majority of that heat energy at the equator. The equator is much warmer than the poles. So most of the sun's energy is going to be absorbed there. So the air near the equator, as it gets warm, remember, just like the water molecules, those water molecules are going to get excited, they're going to space out, and they're going to become less dense. So as that air mass near the equator warms, it's going to become less dense and it's going to rise up. And as it rises up, it's going to leave this void, right? As that air rises up. And so air from the adjacent areas is going to get sucked in to replace that rising equatorial air. And that's what creates the wind. The air that from those adjacent areas that's getting sucked in. to replace that rising equatorial air. That creates the wind. But of course, the winds aren't coming straight in. They're bent due to, you know it, the Coriolis effect. So here's I meant to move this up. Sorry, this is just another video on the Coriolis effect. If you want a little bit more information on the Coriolis, I'm not going to play this again. But sorry, this was supposed to go before my other wind pattern one here. So here's the wind pattern ones. So what you can see here is the warm air is rising up at the equator, right? As it becomes less dense, it heats up, becomes less dense. And as it rises up, let me see if I can get my pen here. Like a pen. I'm going to do it in red here. So as it rises up, right, that air is moving up and rising up, it leaves this kind of void here. So it's going to suck air in from the higher and lower latitudes. But it's not going to come straight in. It's not going to pull that big air mass from below straight in because it's going to move towards the right. It's going to be bent to the right because of the Coriolis effect, because the Earth is in motion, to the right in the northern hemisphere. So if you put yourself, if you could put your head and your arms here, Superman flying down in towards the equator here, you can see that you're going to move towards the right in the northern hemisphere. And that's why your winds, instead of coming straight in, are going to be arced like this, to the right in the northern hemisphere. And here you can see it's going to be moved towards the left in the southern hemisphere. And this is what creates your major trade winds. Okay, our major wind patterns is this fact that the winds are going to be deflected by the Coriolis effect as they approach the equator at about a 45-degree angle. 45-degree angle moved towards the right in the northern hemisphere and the left in the southern hemisphere. Okay, and that's what's going to create our trade winds, our major wind patterns that are created by this rising air mass and then the sinking of cold air. And the trade winds are by far our steadiest wind patterns. You're going to see there are other winds driven by, again, the same solar energy patterns, our westerlies and our polar easterlies, but they're going to be a little more variable. Our trade winds are going to be our steadiest winds. So here's our trade winds. Here's the northeast trades and the southeast trades. So again, we're going to get the same thing happening here with air masses rising here and then air moving in to take its place. So that'll create our westerlies here and here. But our trade winds are going to be our most consistent wind patterns. So again, our polar easterlies and westerlies, those are going to vary a little bit more. So there are some great videos that we have on. I'm going to go ahead and go back to just my pointer here. So I do have some great videos on wind currents creating surface currents, and I'm going to show you one of them, but please watch the other one at home. So let me go ahead and skip. Sorry, again, I have to go through the advertisements for some of these. So this is a great one. I know he's a little monotone, but it's a really great animation. So stick with it here. Yeah, so you'll see it'll sink here at 30 north south. Now, what's interesting here that I didn't talk about is when that warm air mass rises here with all the moisture, it's as it rises up to, in the atmosphere and it cools, it's going to dump all of that water and precipitation, because as it cools, it's not going to be able to hold the water. So it'll dump a lot of its precipitation right here around the equatorial regions and the tropics. So as it continues to move, that air mass continues to move, what ends up happening is by the time you get to 30 degrees north and 30 degrees south latitude, this air mass is pretty dry as it sinks. And as it sinks here, at 30 degrees north and 30 degrees south latitude, this is a really dry air mass. And as it sinks, it will heat up as it gets closer to the Earth's surface. So this is typically, again, 30 degrees north, 30 degrees south, where we typically find more of our desert regions. Okay, sorry about that. So again, moving to the right in the northern hemisphere and to the left in the southern hemisphere. So down here. Okay, so hopefully that's a great animation. Oh, sorry about that, guys. Sorry about that. And so please, if you can, you can watch this one a couple times. There's another video. It's on the exact same thing, but just a different presentation of that video. And I'll let you watch that there if you so need it. And again, you can watch those a couple of times if you need to, or if you're really familiar with this already, then you can kind of skip over this section. So how do trade winds affect currents? So let's talk about this. So our major trade winds are going to create our major oceanic currents. And so the major winds that we have, our trade winds, are going to push the sea surface, creating these major currents. And as the wind pushes across the surface of the water, that uppermost water layer is going to move off. But it's not, again, going to move just straight ahead. Because of the Coriolis effect, it's going to move at a 45-degree angle from the wind direction. Pushed 45 degrees to the right in the northern hemisphere, 45 degrees to the south in the southern hemisphere, due to the Coriolis effect. So each deeper layer, as we go down, and I'll show you this in a minute, it's called Ekman transport. As you move down, each deeper layer is going to move farther to the right in the northern hemisphere and farther to the left in the southern hemisphere due to the Coriolis effect. So this is what this looks like, and we call this Ekman transport or an Ekman spiral. Named after the scientist that discovered it. So what happens is the wind is going to push across the surface. And then here in this case, right, as it pushes across the surface, it's going to push that surface water. And as it pushes and moves down here, pushing across that surface water, it's going to move that water in the direction of net transport 45 degrees here to the right. And this is called our Ekman spiral. So this again is due to the Coriolis effect. Now in this case here, what hemisphere, right? Oops. You can't see it. I had it across here. But I do ask you the question here. What hemisphere is this? If The wind is pushing across the surface, transferring that energy, pushing the surface water, and then as it pushes that surface water, it's going to arc 45 degrees to the right. So if it's to the right, you got it, it's in the northern hemisphere, okay? If it were to the left, if it were to spiral this direction and the net transport were this way, then it would be in the southern hemisphere. So this is actually in the northern hemisphere. So here our wind is pushing across the surface, our trade wind is pushing across the surface water, giving us a net transport movement of the water column, perpendicular, almost perpendicular here, 45 degrees from the wind here to the right. So that's called Ekman transport, just transferring that energy into the water column. And so what you're going to see here, I'm going to go back and use my pen again, and hopefully this will help you to kind of see this. So you're going to see again, our trade winds, remember, coming in here at an angle. So now as it pushes that water column, it's going to move that water column even farther to the right. And that here is going to push this water here, again, farther to the right, creating what's called an oceanic gyre, okay? And so it's going to push this warm equatorial water away from the equator. Here you can see it's doing this here, right? In the southern hemisphere with these trade winds coming in, pushing again this water farther to the left, right? From those trade winds in the southern hemisphere. And so this is going to create these big oceanic gyres. And what that's going to do is that's going to create these kind of patches of warmer water and cooler water in different areas. So for example, here you can see again the same oceanic gyre. Again, here's your trade winds coming in. Then due to Ekman spiral, Ekman transport, it's going to create this 45-degree movement of the water column or current to the right here in the northern hemisphere and push that, again, equatorial water up and around here, the east coast of the United States here. And that's going to push that warmer water up here, creating what's called the Gulf Stream, right? Pushing that warm equatorial water up. Now, as that water gets pushed up here, there's going to be cooler water up here that's going to get pushed down. We call these big oceanic gyres, major surface currents of ocean water. And these cooler waters will then be pushed down here because of, again, Ekman transport, because of those winds, trade winds up here, or the westerlies up here. And that will push that cooler water kind of back down in to fill its place here. Now, what that's going to do is that's going to create, here you'll see on the east coast here, these warmer waters here up against the coast here. And this is why you're typically going to find coral reefs in this environment. This is why you have these warmer waters, because of this current here. Now here, if you look on the west coast, it's going to be just the opposite here, because as these warmer equatorial waters, the current to push away from the west coast, right? And up here over by Papua New Guinea and Indonesia, then the colder waters, okay, from up above here are going to be pushed back down and up against the coast, the west coast here. And because of that, that's going to create these colder waters in the Pacific here up against the west coast. And this is typically why you have kelp forests here and not coral reefs, because you're going to have much colder water temperatures because of this big oceanic gyre. So again, these oceanic gyres are these major surface currents that are created by our trade winds and an Ekman spiral. So pretty cool. If you didn't kind of know how this works. And again, this is really important to understand because this determines why we have certain habitats in certain areas. So this determines, again, why we have here coral reefs in this area, at the same latitude that here we have kelp forests. Okay? So it's all because of these oceanic gyres. So you can see the same thing here again. And this shows you some of the average surface temperatures associated with these oceanic gyres. So you can see again, much colder waters here at the same latitude versus over here, much warmer waters. And it's because of that big oceanic gyre, those oceanic gyres. Now, what ends up happening is in these big oceanic gyres, we found that trash actually gets trapped in these big oceanic gyres, creating these big trash islands. And so I'm going to let you watch a short video on these big oceanic gyres and the formation of these garbage patches. Sorry, sometimes these videos don't quite start the way I want them to. Okay, so that just shows you a little bit on some of those oceanic gyres. There's another video here. I think this is a little bit of a longer one, so I'm not going to show you the whole. Of course, there's a commercial with this. So here, let me see. Yeah, this one's a little bit longer, so I'm not going to show you this. So you can watch this video and they'll continue to talk. I know my video is running a little long here, so I'm not gonna have you watch this whole thing, but it's a short video. Please watch it on the formation of the ocean garbage patches. You can see, you know, plastic pollution has become a big problem for us in terms of our oceanic communities and definitely our oceanic marine life. So please check that out. Ocean currents, okay? So water's really great at transporting heat. And do you remember why is it that water's so great at transporting heat? It's its high heat capacity. Water, it takes a lot of energy to change the temperature of water. to either warm it up or cool it down. So it takes a big input or a big loss of energy, heat energy, to change the temperature of water, much more so than air. And so our ocean currents are going to help warm the poles and cool the tropics with these big oceanic gyres. And this helps to regulate our Earth's climate as a whole. So the Atlantic North Equatorial Current, which I'll show you in just a minute, the currents are driven by these warm waters, again, being pushed away from the equator, and more tropical organisms are going to be found in those areas, as, like we just talked about, up against the coast of the United States, and we're going to find more coral reefs in that area. Now in the Pacific, our North Equatorial Current is driven by these cold currents flowing back down against the west coast, and we're going to see more cold loving organism like kelps. So again, let me just go back and show you that. So again, that was just talking about here. You're going to see more of your kelp forests here versus your coral reef communities in the warmer waters here. Okay, so that's just kind of summarizing some of that. Gosh, I know this video is when I'm just going to try to squeeze in upwellings and downwellings. I apologize. I try to keep these videos shorter, but I want to go ahead and get upwellings and downwellings in here. Oceans also mix between depth as well. So remember, we have to think 3D, right? So we have things called upwellings and downwellings, and this is what's going to help overturn. We call this overturn of water, bringing water up from the bottom, the very bottom of the ocean, up, and then bringing water from the top down. And this overturn usually occurs in kind of our temperate and polar regions, especially during winter when the surface water gets really cold. And why is that? Because as that surface water gets really cold, what does it do? The water molecules pack in tight and they become dense, more dense than the water below as they get colder and colder and colder. And so as that water at the surface gets colder than the water below it, it sinks because it's more dense, and it creates what's called a downwelling, a downward movement of that water. And this will displace the water from the bottom and push it up. So this is a way of actually mixing the ocean. It brings this descending water is going to bring oxygen from the surface down to the bottom. And then it's also going to transport nutrients of like dead and decaying stuff, dead and decaying matter from the bottom to the surface. So it's this overturn is a great way to mix the ocean, bring nutrients from the bottom up to the surface and oxygen from the surface down. So we call that overturn. Now, there are these things called coastal upwellings, and these are important to understand because these are really important to fishing communities, okay? So this mainly typically occurs on the east side of ocean basins, and the winds will typically, when the winds are going to blow parallel to the coast. As those winds blow parallel to the coast, then due to Ekman transport, right? It's going to push the water offshore as it transfers its energy into the water column. In this case, it's moving to the left. So it's going to be in the, which hemisphere? Southern hemisphere, okay? If it's pushing, the wind's pushing across the surface here and then transferring, if you could be Superman across here and put your body on the wind there, you're gonna push this water column towards the left, okay? And so as you move this surface water, okay, offshore, can't just have a void here, right, of where it pushes that water offshore. So water from below is going to fill in its place. And that deeper water that rises to fill in its place is going to bring nutrients from the bottom to the surface. This makes for great fishing, okay? So because it creates this nutrient soup in the water. So coastal upwellings are really productive areas. They're really great areas for fishing. And I'm going to show you a real quick 15-second. There's lots of videos on upwellings. Please watch them. They just take a few seconds. But sorry, excuse these. I wish I could do this without the ads. So this is a great 15-second animation. is a coastal upwelling. So, oops, I guess that was it. So that's your coastal upwelling. And so it'll create, again, a really rich area for fishing. So there's all kinds of videos on upwellings here. Please watch them. There's this cool demonstration. I'll show you real quick. This cool demonstration on upwellings and downwellings. Yeah, so please watch. I'm going to see if I can fast forward through this video when he actually is going to create. Here's going to be his offshore. He's going to create his offshore current. So let's see if we can fast forward here. So here it's pushing those nutrients up, and that's your coastal upwelling. So it's kind of cool to actually be able to see that in a demonstration. So again, please watch the whole demonstration. It's a really cool demonstration. I know I just zoomed through that, but it's a really great demonstration on coastal upwellings and downwellings. And this is just another image to show you, again, this upwelling here is the wind pushing, creating those surface waters. It doesn't do a great job because it doesn't show you the angle of the wind. The wind should actually be perpendicular to the coast. Then Ekman transport is going to, so there's a little minor error here, but if you put the wind direction in the right direction, and then via again, if it was parallel to the coast and then via Ekman transport, you're going to push and create surface waters moving offshore, and then an upwelling bringing the nutrients to fill that place along the coast. And that is where you're really going to create this nutrient soup, which is a great place to fish. Okay. We also do get equatorial upwellings, and that's just because of these, equatorial gyres that we have, again, with a hot air rising. Remember, creating the trade winds, and the trade winds again are going to create this push via Ekman transport of the equatorial waters away from the equator. As those equatorial waters are pushed away from the equator, deeper water is going to move up and take its place, and that's going to bring in some nutrients to the equatorial regions, which is great. This just shows you the distribution of solar energy. I think most of you probably already know some of the distribution of solar energy. And then I'm going to go ahead and stop here. I will go ahead